Welcome to the tutorial on running quantum chemistry simulations in Viking. In this video, we will be performing an infrared spectroscopy calculation on acetophenone. The infrared spectroscopy task is used to investigate the vibrations in a molecule and in particular to calculate the energies associated with the vibrational energy levels. From the calculated vibrational energy levels, a spectrum may be produced that may be considered a unique fingerprint of the chosen molecular structure. Since vibrational transitions have energies in the infrared range, this form of spectroscopy is known as infrared spectroscopy, or IR for short. The individual vibrational modes are associated with certain symmetries in the molecular structure, and certain functional groups are known to interact with IR radiation in certain frequency ranges. Carbonyl groups, for example, are known to have a strong absorption band around 1,700 inverse centimeters, while some aliphatic modes absorb around 3,000 inverse centimeters. Infrared spectroscopy is therefore a powerful tool to identify molecules. As a further example, consider a water molecule. It has three vibrational modes, which can be described as a symmetric bend, a symmetric stretch, and an asymmetric stretch, as you can see here. You can also see the frequencies at which these vibrations occur in its infrared spectrum. The frequencies associated with vibrational transitions depend on the mass of the atoms. If we instead consider heavy water, where the deuterium isotope of hydrogen is used instead of just a proton, the spectrum would instead look like this. Note how the vibrational frequencies are shifted due to this small change in atomic masses. To perform an infrared spectroscopy calculation on a molecule, Viking relies on the Gaussian software to compute the normal vibration modes in the molecule and their corresponding frequencies. This information provides an IR spectrum, and Viking can then visualize all of the vibration modes, as will be shown at the end of this tutorial. Before we start, you should create a project to contain the tasks you create during this or other tutorials. Go to the Projects menu and select New. Name it Viking Tutorials and click Create. Now you have a project to contain your tutorial tasks. The next step is to click New Task in the upper left side of the screen. Here you can see all the possible types of tasks you can run. Expand the Spectroscopy section. Now select IR Spectroscopy. Choose a task name. We will keep the default name for the purpose of this tutorial. Now we need to specify the structure we would like to use. You can add a new structure by clicking New Structure. Here you can upload a structure from your computer. This can be, for example, an XYZ or a PDB file. You can also construct your own molecule with the Viking Structure Editor. We will go through this process in another tutorial. Once you have uploaded a molecule, you can always use it again in another simulation. Here we will be using a previously uploaded molecule. To obtain a reliable IR spectrum, it is important to provide the program with a structure that has been previously geometry optimized. Please see our geometry optimization tutorial for more details on how to do that if you're not sure. You will now specify your calculation method and basis set for the IR spectrum calculation. When choosing these settings, please be aware that if you use a different method or basis set than in the geometry optimization, there will be some abnormalities in the final results. These are fairly minor, and they mainly consist of misplaced peaks in the negative range of frequencies. You can also divide your molecule into fragments and select the charge for each fragment. See the tutorial on geometry optimization, where we show how to select fragments. You are now done with the wizard, and you will see the summary page where you can review the settings for the simulation. Select the resource you want to use for running the simulation. Resources in Viking refer to supercomputers, so if you have not added any resources to Viking yet, you should watch the tutorial about using supercomputers. Click Run Task and you're done. If you go to the dashboard, you can view the status of the tasks you have started. The new task may be queued for some time before it can start, since the requested number of nodes on the supercomputer must be available before it can run. Grab a cup of coffee, sit back and relax for a while, since it may take some time for the task to complete. Once it is done, go to the Task Overview page by going to the dashboard and clicking on the task, or selecting the project that contains the task and then clicking on the task. On the Overview page, click on the View Results tab. Here you can view the results of your simulation. Your simulation generates a great deal of information, for example, the IR spectrum for your molecule. Looking at the graph of your IR spectrum, you can see the vibration frequencies on the x-axis and the intensity of those absorptions on the y-axis. In order to illustrate the correspondence between calculated and experimental IR spectra, consider here two spectra of acetophenone. In experimental IR spectra, the transmittance is measured. However, in calculated IR spectra, the oscillator strength is calculated. These methods result in slightly different graphs, but the key information, the positions of the major peaks, should coincide, as they do here. You can also use the structure viewer to see visualizations of some of the results. Here you can visualize the relevant normal vibrational modes and identify those specific ones that correspond to the enhanced peculiarities in the computed IR spectra. These vibrations are said to be IR active. Consider, for example, the peak at around 1,300 inverse centimeters in the spectrum of acetophenone. As you see, this peak with high IR activity corresponds to a specific vibration where most of the atoms in the molecules experience coherent oscillation. The activity of specific molecular vibrations in the IR spectrum can be understood and described through molecular symmetry, but this is outside the scope of this hands-on tutorial. For further reading, we would recommend these materials. Now that you have an IR spectrum of your molecule and can visualize the various vibrational modes, you're done with the IR spectrum calculation in Viking. Feel free to contact us if you have any questions or problems about using Viking.